Good afternoon. I'm Lara Tomholt. I'm a postdoctoral researcher at Princeton University, and my work focuses how we can use cement-based 3D printing to create building components with enhanced functionalities. And today I'll be presenting on the extrusion-based 3D printing of channel networks with cementitious materials. Implementing channel networks into building materials or other internal cavities can be helpful in a wide range of applications. For example, they have the potential to increase a component's thermal performance by creating cavities in which you can insert insulation materials or phase change materials. Or they may allow for the transport of fluids, such as water in heat exchange systems or precursors in self-healing concrete. They can also provide pathways for post-tensioning reinforcement or pathways for other infrastructures such as utility pipes or cables. And lastly, they could potentially reduce material use without structural disadvantages. To develop these components, we can draw inspiration from nature, which has proven to have remarkable structural properties and efficient transfer of heat and mass. However, as we see in these images, for example, in leaf venation, these systems can become quite complex. They have many channels branching and reconnecting in different orientations, and this makes them challenging to engineer in cement-based components. For example, to cast them would require highly complex molds. On the other hand, 3D printing techniques with support materials are available, for example, particle bed 3D printing or multi-material 3D printing. But those face the difficult, if not impossible, challenge of removing support materials from those narrow, interconnected, or even enclosed channels after printing. So extrusion-based 3D printing without support materials can be considered a more suitable method of fabrication. However, its most significant challenge is the absence of support structures inside those cavities. In this video, we're printing a sample with multiple channels, and you can see that these unsupported filaments will undergo early age deformation, and that will significantly change the shape and size of the channel, perhaps even block it or completely collapse the channel. And for channels with smaller inclinations relative to the build plate, as you see on the right, if we use horizontal toolpaths, those overhangs can become quite significant. And unfortunately, available slicing algorithms exclusively generate horizontal planar toolpaths. Due to these challenges, fabrication of 3D printed channel networks of cementitious materials has been limited. They are often large scale, relatively disconnected, and relatively vertical to the build plate. Even fewer are examples of channels printed using non-horizontal toolpaths. And for these kinds of prints, a formalized framework to select appropriate toolpath angles is missing. For smaller and interconnected channels, researchers are exploring plastic 3D printed channel networks that are then cast in cement rather than actually building in those channels ourselves. So we set out to develop new strategies to tackle this challenge of overhangs and advance our capability to 3D print channel networks. Opportunities arise when customizing the planar toolpath angle. In our research, we explored the relationship between the channel inclination alpha relative to the build plate, the channel diameter d, and the toolpath angle beta relative to the build plate. In our assessment, we considered only overhangs above the channel cavity as a result of the absence of support structures inside that cavity. And we also only considered individual filament deformations. So we did not consider, in this study at least, a filament deformation due to other phenomena such as yielding, buckling, or the compound effect of those local filament deformations on global channel stability. To approximate filament deformation across an unsupported span, researchers have used the simply supported elastic beam model. Assuming linear elasticity and uniformly distributed load across the filament, we can obtain the bending moment M at the midpoint of the span using this equation. Higher values of the bending moment can lead to greater deformations. While the bending moment doesn't quantify the actual deformation, the advantage of using it is that we can easily obtain the parameters that it uses, namely the overhang volume V and the span length L, from 3D modeling software. And this alleviates the need to perform material-specific studies and allows for rapid early assessment of channel stability just during the early stages of design. So we developed an accessible high-throughput workflow in Grasshopper, which is a parametric modeling software. And this workflow allows the user to rapidly model a channel network and obtain its bending moments M. It has a series of automated steps. First, it models the geometry of the channel for a given channel inclination and diameter. Then it generates the toolpaths with the desired toolpath angle beta. And then it models the filament geometry from these toolpaths. Then the script extracts the overhang geometry, obtains the overhang's volume and span length, and calculates the bending moment M of each overhang. To optimize the toolpath angle for 3D printing, the script allows one to automatically run through a series of toolpath angles and returns the one resulting in the lowest M values. The parametric nature of the script allowed for a rapid calculation of M for a large series of channels, for varying channel inclinations alpha and varying toolpath angles beta. Here we're showing the results for a channel with a diameter of 6 millimeters and channel inclinations ranging between 0 and 70 degrees and toolpath angles ranging between 100 and 180 degrees. As I mentioned previously, the reported M values are not an explicit prediction of filament deformation, but you can see that they do provide an assessment or a comparative assessment of overhangs for a given channel inclination alpha. To compare the script's results to 3D printed objects, we printed multiple single channels using an Ultimaker printer. We use cement paste with a water cement ratio of 0.27 and a composition that's shown here. Two of the channels we printed had a diameter, an inner diameter of 6 millimeters and a channel inclination alpha of 15 degrees. And we printed them using a toolpath angle of 180 degrees, which is shown here in A, and 135 degrees, which is shown here in B. And the sample with 180 degree toolpath angle was printed using a straight nozzle. The sample printed with 135 degree toolpath angle was printed using a nozzle with a 45 degree angle to prevent the nozzle from going through recently deposited filaments. The Grasshopper script calculated that the 180 degree toolpath angle would result in greater overhangs and thus a higher bending moment. And indeed, we saw in the results that this channel experienced considerable deformation of the channel internal cavity. We also printed channels with a channel inclination alpha of 0, so parallel to the build plate. For these channels, the analysis shows that a toolpath angle beta of 165 degrees, which is shown here in A, would result in larger overhangs than a toolpath angle of 120 degrees, which is shown here in B. And we indeed saw that the 3D printed channel of the 165 degree toolpath angle showed higher deformation of the cross-sectional shape, as you can see in these images of the taken during printing. After the tests with single channels, we further expanded the Grasshopper script by including the capability to generate channel networks rapidly. The input in this automated modeling sequence is a collection of points. From these points, several types of 2D and 3D networks can be generated, for example, branching, interconnected networks, or separate channels. And then the channel geometries are modeled by specifying a channel radius and optionally applying Murray's law. Next, this automated design sequence follows the same steps that I presented earlier. It models the toolpaths and the filament geometry and then extracts the overhangs and calculates the bending moment M found among all overhangs. The script also automatically generates G-code for 3D printing. The script allows the user to automatically run through all toolpath angles and returns the angle that results in the lowest M values and most likely will result in a successful print. For this particular design, the lowest M values can be found between 120 and 160 degrees roughly. The script visualizes the overhangs with a color gradient, and that allows the user to easily identify areas that are perhaps a little bit more problematic and adjust the network design if desired. To demonstrate the capabilities of this script, we generated several biologically inspired channel networks designs and 3D printed them. The first sample, sample A, is modeled after the many dichotomously branching channel networks that we can find in nature. It features a small network of channels with varying channel inclinations alpha and varying channel diameters that adopt Murray's law. Due to its somewhat symmetrical design, the script suggested using a toolpath angle beta of about 0 degrees would result in the lowest M values. And after printing, we could indeed see that the channel openings on the side and bottom of the print remained open. We more closely examined the channel cavities on the interior of the print and confirmed with micro-CT data that the channels remained unobstructed. We also imported the micro-CT volume into our Grasshopper modeling software and aligned it with the 3D model that we made initially. This allowed us to qualitatively compare the shape and size of the model channel, which I'm showing here in C, with the actual 3D printed channel, which is shown here in D and highlighted with a dotted outline in C. And we see that the channel cavity of the 3D print matches relatively well with the actual 3D print, with the actual model, even though it's perhaps slightly narrower in this direction. And in future studies, we would be able to perform a more comprehensive quantitative analysis of the actual filament deformation that occurred during the printing. Our next sample, sample B, was inspired by leaf venation and features a bit more of an elaborate network of branching channels with a channel inclination alpha as 0, so parallel to the build plate, and a triangular cross-sectional shape. And we 3D printed it with a toolpath angle beta of 0. We designed it in a way to have the bottom remain open so that we can very easily identify if the channels remained unobstructed during printing. And the last sample I will show you is this one, where we explored a 2D array of semi-ellipsoid parallel channels. The Grasshopper script instructed to use a toolpath angle of 120 degrees to minimize overhangs. And indeed, this video shows that there was considerable stability during printing. As I mentioned at the start of my presentation, one of the potential uses of these 3D printed channel networks is to transport fluids, and that's something we're demonstrating in this video. And this can be helpful in a wide range of applications, for example, radiant heating and cooling systems or self-healing concrete. So in short, our Grasshopper workflow rapidly models complex channel networks and optimizes the toolpath angle for print fidelity. And this capability advances the process of designing and 3D printing these channel networks that are similar as those that we see in biology. And these new types of 3D printed cement-based channel networks can advance the functionality and marketability of 3D printed cement-based components. While our samples were millimeter scale channel networks, the same workflow can be applied to larger scale channels, as well as other types of void geometries like shells. We've made the scripts available on GitHub, and we also created instructional videos on how to use them. And the results that I presented today have been published in RILEM conference proceedings. Of course, future research is needed. especially to assess the suitability of using the metric M to determine print fidelity, as well as understanding the effect of yielding, buckling, and the sliding of filaments that is printed at channel inclinations larger than 0. And lastly, future developments of the script would include the option to model non-planar toolpaths, which could further expand the design space and print fidelity. I'd also like to take the time to recognize the several sources of funding that supported this research, most notably the Distinguished Postdoctoral Fellowship from the Andlinger Center for Energy and the Environment at Princeton University. Lastly, I'd like to highlight that my work on 3D printing of channel networks is only one of the many architected materials that our lab has been investigating. As a bit of a background, architected materials are materials that have tailored geometries, giving them properties that exceed those of their constituent materials. Graduate students and postdocs in the lab have studied biologically inspired architectures that they fabricate using extrusion-based cement 3D printing, as well as other advanced manufacturing methods. And the exciting quality of these architected materials is their fracture toughness, which outperforms costs of the same material. And if you're interested in learning more about these, we're happy to discuss them with you. With this, I'd like to thank you very much for your attention. I'm happy to answer any questions you may have.